Ever wonder what's really protecting your bank account or keeping your private messages, well, private? It's not some kind of digital magic. It's math. And more specifically, it's a branch called number theory. Today, we're going to pry open the mathematical toolbox that modern cryptography is built on. We're not just going to look at the locks. We're going to understand exactly how the keys are made.
Think of our time here as your personal cryptographer training mission broken down into 3 parts. First, we're going to forge the keys by getting a handle on the essential tools. Then, it's your turn to face the locks, a series of encrypted messages. And finally, I'll give you the master hints, the inside scoop you need to decode them. Let's get started.
Okay, so part 1 is all about the fundamentals. This stuff, it's the absolute bedrock. These are the core principles that every single cryptographer needs to know like the back of their hand. After all, you have to learn how to make a key before you can even dream of picking a lock.
First up in our kit, prime factorization. This right here is the fundamental theorem of arithmetic. And trust me, it's a huge deal. It basically says that every whole number has its own unique secret identity, a set of prime building blocks. It's like a number's DNA. For 360, that DNA is 3 2s, 2 3s, and 1 5. So why does this matter so much? Well, it's because multiplying primes together is super easy for a computer. But going the other way, factoring a massive number back into its primes, that is incredibly, incredibly hard. And that difficulty, that's the first lock we're going to learn how to use.
Now, what's really cool is we can use that prime DNA to do some other neat tricks, like figuring out how many divisors a number has without the pain of listing them all. Let's take 360 again. Its prime DNA was 2 cubed, 3 squared, and 5 to the power of 1. The formula is crazy simple. Just look at the exponents, 3, 2, and 1. Add 1 to each of them, so that gives us 4, 3, and 2. Now just multiply them together. 4 times 3 times 2 is 24. Boom! 360 has exactly 24 divisors. It's an awesome shortcut.
All right, our next tool is called modular arithmetic. I know, it sounds super intimidating, but stick with me, because it's really just clock math. You see, instead of numbers just going on and on forever, they wrap around once they hit a certain value. We call that value the modulus. On a standard clock, the modulus is 12, right? Once you hit 12, you just start right back over at 1.
And this is a perfect example of why it's so powerful. If someone asks you what time it'll be in 100 hours from 3 o'clock, regular math just gives you 103 o'clock, which helps nobody. But clock math focuses only on what's left over, on the remainder. We just need to find the remainder of 100 divided by 24. That remainder is 4. So 4 hours after 3 o'clock is 7. See? It's all about finding that useful little leftover piece.
Okay, our final key is for a very specific but very cool problem: finding how many zeros are at the end of a huge factorial. A factorial is just a number times every whole number smaller than it. So for something like 100 factorial, the secret isn't about counting tens, it's about counting the prime factor 5. You see, every 5 pairs up with a 2 to make a 10, and that gives you a 0. And since there are way more 2s than 5s, the 5s are the limiting factor. This formula lets us count them up fast. You just take your number, divide it by 5, then 25, then 125, and so on, and add up all the whole number results. And when you run that formula for 100 factorial, you get 24. That's it. 24 trailing zeros. I mean, stop and think about that for a second. We didn't have to calculate a number with more than 150 digits. We just used a clever pattern. That's the real power of number theory. You find that hidden structure, and suddenly the impossible becomes pretty simple.
All right, you forged the keys. You've mastered the tools. Now, it's time to face the locks. I'm about to present you with 4 encrypted messages. Your mission, should you choose to accept it, is to use everything we just talked about to crack them. You ready for this?
First up, message number 13. This is a big one, an exponent problem. What is the remainder when 3 to the power of 100 is divided by 7? A calculator won't save you here. You're going to need that clock math. Next, message number 14. For this one, you've got to think backwards. We need the smallest positive number that has exactly 6 divisors. That divisor count formula is going to be your best friend here. Message number 16 is a classic remainder puzzle. There's a mystery number out there. When you divide it by 3, you get 2 left over. When you divide it by 5, you get 3 left over. What's the smallest positive number that fits both clues? And finally, the boss level, message number 18.
What is the very last digit of this absolute monster of a number, 7 to the power of 7 to the power of 7? It looks terrifying, I know, but just remember your training. There is a pattern hiding in there. You just have to find it.
Okay, let's switch gears. For this last part, I'm not going to just give you the answers. I mean, where's the fun in that? A true cryptographer learns by doing. So instead, I'm going to give you a detailed hint for each message. Think of it as the master key, that little strategic nudge you need to unlock the solution for yourself.
For message 13, that big 3 to the 100 problem, the hint is one word: cycles. Seriously, do not try to actually calculate that number. Instead, just start working out the remainders when you divide by 7. What's 3 to the 1, 3 to the 2, 3 to the 3? You'll find a pattern that just keeps repeating. The length of that pattern is everything you need.
For message 14, where you need to find the smallest number with 6 divisors, you've got to reverse engineer that formula. We know the final answer after multiplying is 6. So what whole numbers can you multiply to get 6? Well, it's either just 6 or it's 2 times 3. That tells you what the exponents must have been before we added 1 to them. So your number either looks like some prime to the 5th power or 1 prime squared times another prime. Just test the smallest primes in those two shapes and see which one gives you the smallest number.
The hint from message 16, the remainder puzzle, is actually kind of funny. Don't overthink it. Just pick one of the rules. Let's say the one about having a remainder of 3 when divided by 5. Okay, what are those numbers? Well, there's 3, 8, 13, 18, and so on. Just start listing them out, and for each one, check if it also fits the other rule. The very first one you find that works for both, that's your answer. Sometimes brute force is the elegant solution. And for that final intimidating message, 7 to the 7 to the 7, the secret is to see it as 2 problems nested inside each other. Step 1, just find the pattern of the last digit of powers of 7. 7 to the 1 ends in 7, 7 squared is 49, so it ends in 9, and so on. You'll find a short cycle that repeats. Step 2, figure out where in that cycle you'll land. To do that, you need to find the remainder of that giant exponent when you divide it by the length of your cycle. It's a cycle problem inside a cycle problem.
So there we have it. We went all the way from the basic DNA of numbers to the strategies needed to decode some pretty complicated messages. And remember, these aren't just abstract math puzzles. These are the fundamental ideas that keep our entire digital world secure. So the question isn't just whether you can solve these specific problems. It's, now that you have the keys, what codes will you choose to crack?